One of the very useful features of spectroscopy, especially nonlinear spectroscopy, is that we can use diagrams to help us depict the light-matter interactions and help us predict what will be the absorption and emission frequencies. Remember that the material response allows us to essentially convert light frequencies from one type to the other type. So if we look at second order, if we think of the second order response as the thing that we're going to detect, right? So the signal field will be driven by the second order polarization. Then this refers to things like some frequency generation spectroscopy or second harmonic generation, which could be used in a spectroscopic way or as a practical tool just for generating light with twice the frequency, half the wavelength. But there are other processes that occur by second order as well. So I'm going to try to show you how you can think about that. Omega s will be equal to plus or minus omega 1 plus or minus omega 2. The wave vector will equal plus or minus k1 plus or minus k2. Right? I didn't derive this, but you saw in the previous formulas that the wave vector and the frequency played exactly the same role. They had a difference in sign due to a convention of classical electromagnetism that's not really that important for us. When we realized that we had a cosine, especially if we have a CW laser, a CW field, then we could switch the signs however we wanted to. All right, so we might consider, so that meant that we would have ultimately figured out that there was a product of cosines with different wave vectors, particularly if we chose a reference time to consider the interference of the laser fields. Okay, and so what we want to do now is consider what happens when we take two fields and interfere them, right? That's one thing that we can try to do. All right, and so what we're going to do is we're going to realize that there's basically a few different possible frequencies that we could have. So if omega 1 and omega 2 are sort of similar to each other, then one signal that we might have would be this signal field, which would be like omega 1 plus omega 2. So the driving fields are omega 1 and omega 2 frequency, and the signal will come at their sum. So sometimes people like to write these kinds of diagrams like this, but they have to do it right. I can get it to work. There we go. So you have basically an arrow depicting an energy or a frequency, right? And going up means that that energy is somehow going into the material. Another way of thinking about it is that the frequency will be associated with a sign. And then the idea is that the signal that emits is going to be often indicated by this wavy arrow. And this signal here, of course, is equal to omega 1 plus omega 2, right? So this is the some frequency generation signal. But what can also happen, of course, is that you can have the difference frequency, right? Because there are four signals here. Now, what about minus omega 1 minus omega 2? I mean, that frequency in terms of magnitude is exactly the same as plus omega 1 plus omega 2. You might have, and so if we assume that system is in the ground state, it's not going to go down farther. So there's not like a negative energy that we're talking about here. So the minus omega 1 minus omega 2 signal is not any different from the plus omega 1 plus omega 2. All right, and so then the other interesting signal for second order will be something like omega 1 minus omega 2, or vice versa. Now, what does that look like? So that looks like omega 1 sort of upwards and omega 2 downwards. Now, if omega 1 and omega 2 are equal to each other, obviously this is just equals 0. But if they aren't equal to each other, then there will be a difference, and then our signal will be the difference between these two. And it will be lower frequency than either one. So this little frequency that comes out is called difference frequency generation. And it has a frequency omega 1 minus omega 2. If this is omega 1, this is omega 2. Now you might be asking, what's up here? Okay, and now that would be in the response function because we're only thinking about the fields. So if this material does not have a resonance at that energy level, then this signal will not have an enhancement of resonance. But one way to think about this is that there's a resonance somewhere, and it's presumably higher energy, right? And there's some tail of that resonance because of dynamics that we'll talk about later that might stretch a little bit to this region of the spectrum. So it's possible that there could be like a pre-resonance or something like that. Otherwise, you're relying on something called the hyperpolarizability, which is essentially an interaction through the electron distribution and how the electric field influences the electronic distribution. So when you go into your lab and make a green light from a near-infrared laser, or simply use a laser pointer to do that, then what's happening is you are interacting with a material, a crystal, which has, generally speaking, a pretty flat frequency response to its optical response. And it's just allowing you to do the sum frequency of 2 near-infrared field interactions to produce 1 green emission. That's some frequency or second harmonic generation. This DFG is actually used in 2 different optical applications in spectroscopy. Depending on where it is on your table and who you are, then this can be called different things, but they are actually the same exact phenomenon. What we usually do is call, I'm going to write it again. We usually call the big one here the pump. Then of the 2 that come down, the higher energy one is called the signal. And then the littler one is called the idler. All right, and if you use this terminology, then we typically call this thing an optical parametric amplifier, OPA. This is the main way that we generate near-infrared light with ultra-fast or even not ultra-fast pulses, even picosecond, nanosecond, and slower pulses. There are different variations of this. Sometimes they're in the infrared or near-infrared. Sometimes they're even in the visible, but this process is exactly the same. It's just how you generate the different wavelengths is different. And so this is a generic tool that allows us to essentially create any combinations of signal and idler that add up to the pump with some technical details of the material that you're using in the laser and all that stuff. So it's a very, very powerful tool for generating light tunable across extremely large ranges of the electromagnetic spectrum, particularly of interest to chemistry. So that's one thing, OPA. Now sometimes people will do is they'll take that signal field and they will send it into another apparatus and also the idler and make them interact again, doing exactly the same process but in a different material that has different technical properties. And then they'll generate even lower energy. And they'll call that difference frequency generation. I actually don't know why they don't just call it an OPA, but for some reason they call it difference frequency generation. And so do we. We do this all the time. This is how we make infrared light. And the frequency of this will be signal minus idler. Right? And then this is a very convenient way to make mid-infrared light when you start with a higher frequency light, let's say in the near IR, like 800 nanometers, which is a typical wavelength for lasers that we use. Now, it's a 2-step process, which seems bad, but actually there's some advantages of doing it in 2 steps. You can choose a material that's better for this and a material that's better for this, number one. Number two, there's some interesting dynamics of the actual amplification process that become enhanced when you can drive them into saturation, and that's easier to do sometimes in 2 steps. All right, so this is a pretty common way for generating mid-infrared light. And it's an example of a second-order nonlinear optical process. Now let's think a little bit about the directions. All right, so remember I said that we have these different frequencies, which is mostly what we've been considering here, but there's also the directions. Now, of course, if everything is collinear, there's nothing to worry about because the wave vectors, which might have different lengths, will still have the same direction. And a wave vector, right, is going to have a magnitude, and then it's going to have a, some components, kx, ky, and kz, in some basis. K is 2 pi over lambda. So that tells you the size. It's proportional to the frequency. And these are the directions. Now, practically, usually in a laser lab, if you're using optical fields, you're focusing in a long direction, and the angle between the beams is very, very small, right? So a realistic view of two beams coming in, maybe like that, into something that focuses like a lens or a mirror. And then they'll cross, and they'll cross really far away. So if you look at the projection of these two vectors, the z projection, which is always the direction that the laser is going, are about the same, even though there's a slight angle maybe that, you know. So we tend to just completely ignore or ignore the z part of this and think of our vectors in two dimensions, just essentially the x and the y components. And that turns out to be quite convenient. All right, so then I can write the length of the vector in x and y, and then I can do some very simple arithmetic or very simple vector addition to figure out which way the beam goes. So for example, if I have some frequency generation, SHG or SFG, I'm going to have two fields pointing in, they could point in the same direction. If they point in the same direction, then I'll just get K1 plus K2 and that's it, and the beam's going to go in the same direction because I'll be adding the same components here. It just doubles or makes bigger the direction part because by changing the wave vector part, the magnitude part, right? But the direction will be the same if they're collinear. As soon as I make them non-collinear though, then that's kind of interesting, because if I make one non-collinear, let's say imagine what that means is I shoot them at my sample or my material at an angle. So in physical space, my beam might look like this, and this is my material. But I don't want to think of the beam wave vectors in physical space because I need to think of them in terms of their wave vectors. So then what I should do is I should write down one wave vector like this, right? And then the other one like this. They will still have the same relative angle as my real beams do in physical space, but this one that has higher frequency will have a longer magnitude, a larger magnitude, right? The actual magnitude of the vector will be longer. So when I add them together, here's my sample. The way I can do that is I can sort of follow my beam through and then add it to this one, but adding with vector addition properly. Something like that. So what's going to happen is my signal that's generated is going to have a slightly different angle because it's going to be the resultant vector of those two things. And in general, just because of the way vectors work, the longer one is going to have a bigger influence over the direction. So your signal will show up closer to the higher frequency thing if you do non-collinear second or some frequency generation. Right? And this allows us to predict where the signal will go, even though it won't show up unless these two fields are interacting with the material at the same time, or roughly the same time. All right, so this is a way of figuring out where the signal will go in physical space. All right, and the vector will be longer than either of the original ones, obviously, because of the way you add the vectors like that. Okay, so that's an example for second order processes. We have some frequency generation. This is non-collinear. And when it's non-collinear, then we get the signal in a so-called background free direction, which can have advantages. It can also have disadvantages. Probably, I don't know if we'll get to be able to talk about that or not, but maybe we will. We can look now at third order. Why am I focusing only on these nonlinear ones? The linear one's pretty straightforward. You have one field, and then the signal just goes in the same direction. So there's no issue about where the signal will go, and there's no issue about what frequency it has because it's the same frequency as your light field. There's nothing nonlinear about the linear response. You cannot change the frequency of light with a linear response. If the material responds linear to your field, the frequency will never change. Okay, so here's the third order. Now, the third order has three terms, so the signal can have omega plus and minus omega 1, plus and minus omega 2, plus and minus omega 3. Right? So there's a whole bunch of different combinations that we already mentioned what they were. If we rule out all the ones that are sort of the backwards versions of the others, meaning like negative omega 1, minus omega 2, minus omega 3, and call that the same as plus all of them, then the main four frequencies that we get out will be omega 1 plus omega 2 plus omega 3. That's the sum frequency. We can have minus omega 1 plus omega 2 plus omega 3. We can have plus omega 1 minus omega 2 plus omega 3. And then we can have omega 1 plus omega 2 minus omega 3. Those are the three different signals that we will get, 4 different signals we will get. And then, of course, you have 4 more, which are just putting minus signs in front of all of these. All right, and again, this is the third harmonic or some frequency signal. And these ones are the ones that, if your frequencies are similar to each other, then your signal will be similar to those frequencies, right? So a very typical application of this might be nowadays with ultra-fast lasers, you'll have 3 fields, 3 pulses. Maybe all 3 pulses actually are generated from the same nonlinear process or nonlinear optics, or it could be generated from second harmonic or just straight out of the laser. If you just happen to study something that absorbs what the laser absorbs, which is not usually the case anymore, then what'll happen is these, omega 1 nominally equals omega 2, and so omega 3 will determine the frequency of your signal. If omega 1, same thing here. These 2 cancel and you just get omega 3. Same thing here. These 2 cancel and you get omega 1 or omega 2, right? Now, if you have bandwidth, that means your spectrum will have bandwidth. That means that there's many different frequency combinations that you can have. Now, there are other kinds of experiments you can do, but we're using more narrowband and tunable lasers. And I'll talk about those as well, of course, because those are very important. And they were certainly very important historically, and they're still important in experiments people do now. All right, so what we want to do is take a look a little bit at what are the types of third order experiments you could do. But I want to show you one particular one. When I was actually when I was just finishing, or when I was at the end of my undergrad and I was looking at, what are things that people do in spectroscopy that's interesting, I was a little bit naive, but I had a pretty good insight, and I was reading some review articles. And I read one review article by Mike Fayer. And it was a paper about, it was a review article, like Annual Reviews or something like that, about a particularly interesting kind of spectroscopy called transient grating spectroscopy. Transient grating spectroscopy. And I wish I could find my old loose leaf binder that had all these papers that I printed out, because that's how old I am. And I know I wrote on the first page, this is the coolest thing ever. I wrote that. This is the coolest thing ever. But I know also from a cartoon that I drew right under it, I didn't understand how it worked. So I have to give great credit to Mike Fayer for explaining it in a way that sounded so exciting to me, even though I really didn't understand what was going on. But I think that's maybe not uncommon for just beginning graduate students or ending undergrads. But now I understand it really well. My wife did her PhD in this technique, and in fact, it's a very useful way of thinking of all nonlinear spectroscopy, even some of the more modern ones. And so the basic idea is actually very simple. You take 2 laser beams and you cross them at an angle. In your sample. And in the simplest way of understanding this, the material is resonant with these 2 different laser beams. It means it absorbs. It has a transition that you can excite directly with these 2 laser beams. Now, there's other ways you can do it where there's not a resonance, but I'm not going to talk about that right now. All right, so now think about what happens when you take 2 fields and you cross them and you interfere them, meaning that you make them do their intensity. You measure their intensity at the place where they interact. What's going to happen is, and I can work the math out of this later, but I just want to tell you what happens here so you can see what's going on. The intensity of this, so what you do is you take those 2 fields that we talked about before, right? EJ, so EJ is going to be E1 and E2. They're the same thing, they just have different directions, right? So one is going to have, let's say, plus K1, and the other one has minus K1 because it has the other direction, the other projection. Think about what that would be, right? So when you interfere the 2 of them, you're going to get a standing wave when you add them and then square them, because that's what intensity means. Take the modulus squared of the field. The field is now E1 plus E2, but E1 and E2 are the same. They just have a slightly different thing, and then you make the square. That's the intensity at this sample here. So what's going to happen? Because of the difference in the wave vector, one's pointing this way and one's pointing that way, they make a standing wave. And then we can pick a dimension that we like. Let's call this x. Okay, and you've probably seen this before. It's not that hard. You can do it with all kinds of things. If you want to make a pattern like this, you can actually just take a piece of hair and put it in front of a laser beam, and you'll get the single slit pattern. It looks very similar to this. If you ever align an interferometer, the way you know it's not aligned is you see these fringes, and then you keep adjusting the interferometer until these fringes go away, and then you know that you've got it as collinear as possible, because the angle tells you the bigger the angle is, the closer together these fringes will be. So the smaller the angle is, the farther apart these fringes will be. And that turns out to also be very important. So now just think about what happens if you take two laser beams and you excite a sample in this pattern with an alternating bright, dark, bright, dark, bright, dark, and bright and dark. What's going to happen is the material properties are going to be different, or the optical properties are going to be different in the regions of the bright and the dark regions. Right? One of the things that's going to be different is the index of refraction is actually going to be different depending on whether you are in the bright side or in the dark side. There's a very important relationship that we can derive later that relates absorption to index of refraction. And once you've already excited the molecule, you will necessarily change its absorption properties again. That's what the basis of nonlinear optics is. And so what the absorption will be here is different from the absorption there. So that on the one hand, you might think, okay, it's dark and bright and dark and bright. So if I send in any material or any laser beam through here, it's going to see sort of maybe dark spot, bright spot, or bright spot, dark spot based on the changes in the absorption spectrum. And that just looks like a normal amplitude grating, the kind of diffraction grating you would use in a spectrometer. It can also change the index of refraction in the sense that the phase changes from spot to spot, from bright to dark and bright to dark. That looks like a phase grating, the kind of like thing that causes interference in soap films. So if I send another laser beam in here, and unfortunately I'm mixing metaphors of my colors, but I don't know if I have a red one that works. Let me try. So what I'm going to do is I'm going to send another beam. Oh, there it goes, it works. And notice I changed the angle with respect to the other two. That's not necessary, but it helps you see what's going on. And then what do I have here? Inside my material, I have this grating. It's like a diffraction grating. So this looks just like a multi-slit interference pattern, like a multi-slit, right, piece of material, like you might have learned maybe in an earlier physics class, or if you haven't seen that, you should look it up. It's a very common kind of interference pattern. And what's going to happen is my beam will diffract. The straight through beam looks like this. And I'm going to get a beam that diffracts. And I can figure out which way it diffracts by knowing the period of the grating. It's going to basically follow the Bragg law. If it's shot straight through, I get one this way and one this way. If I shoot it at a bigger angle, I get one over here, and I'd actually get another one over here. I just ran out of space to draw it. All right, and why do I get those two different patterns? The reason I get those two different patterns is because of all these different signal combinations here. Right? One thing you'll notice is, what about these two? I have my two fields. They both have the same frequency. So the frequency will cancel, and I'm just going to get the frequency of whatever this is. So if it's redder, longer wavelength, then it'll be longer wavelength. Whatever it is, I will get the frequency of omega 3 for my signal. What about the Ks? So one signal that I'm going to get out, let's call it K plus, will be equal to plus K1 minus K2. And the other one I might call K minus will be minus K1 plus K2. Okay, and what's going to happen is this is just going to change the direction of my interference or my diffraction. So we tend to call these, if it was a diffraction grating and I wasn't doing nonlinear optics, I would call these orders. I might call this the +1 order, and I might call that the -1 order. What about the +2 and -2? I can do that too, but I need fifth order response to get that to work. All right, so the point is that we have two different signals that are essentially identical looking here. And for the practical purposes, when you do this kind of experiment, they are exactly equivalent to each other. But then they give me, in the diffraction, a measure of how much modulation this diffraction grating has. Okay, so here's where the exciting part comes. Imagine we have a time delay between the pulses that make the diffraction grating. So these two are time overlapped, but then our probe has a time delay, whatever it is, delta t. All right, so what we can depict delta t as sort of the length of this arrow. Okay, and so then what we can do is we can monitor how this interference pattern written into the material changes as a function of time. Because imagine what we did in here was we just excited some molecules to an excited state, some dye molecules, for example. And then what would happen over time is those dye molecules would relax back to the ground state again. As they relax back to the ground state, they start to look like there's not as much of a difference between the dark and the bright spots, right? So over time, the diffraction grating will switch and look something like this. And it's the contrast in absorption or refraction that between the bright and the dark spots that determines my diffraction efficiency. So if I was just to calculate or just to plot diffraction efficiency, which I might call eta, for example, it's a common abbreviation for efficiency, as a function of the time delay between my excitation pulses that wrote the diffraction grating and my probe, I will probably see something like this. At time 0, the signal will get very large because the effect is turned on right away with my, let's say, short pulses of some sort. But then some dynamical process might occur. So maybe there's, for example, a process where my electronic excited state, now we can just start to draw kind of cartoons, but they combine all the ideas that we've been thinking about. Maybe this system goes to the excited state and then it kind of relaxes for a bit. And then maybe it has a way of getting down to the ground state. So perhaps it could fluoresce, or perhaps it finds some other path that gets down that's non-radiative. We don't know because we're not going to see that. What we're going to see is as the system relaxes to the ground state, maybe with different time scales, we're going to see a change in the diffraction efficiency as a function of time. All right, the diffraction efficiency as a function of time will tell us about the nature of the excited states and how long they stay there as we go back down to the ground state. Okay, and the cool thing about this is that, although not from the way I've described the experiment here, if you measure this with another field and interfere with this signal field that you're detecting, which we'll talk about much later, it's very important but to sort of technical point, then you can actually also separate out the parts of the grating that comes from changes in absorption from the parts that comes out from the changes in dispersion or the changes in the index of refraction. And that's something that's very difficult to determine separately experimentally from just measuring the change in absorption, which you would do if you did a pump probe transient absorption experiment. All right, so this is called a transient grating. You can measure, the cool thing is also you can measure this decay of the grating intensity or the grating contrast with a laser pulse. It's not resonant with the material at all. So you can use a non-resonant probe and just rely on, and that helps you actually isolate the part that's just based on density. All right, and you might say, what good is that? Why would you ever want to do that? So I'll give you an example of that from the PhD research of my wife, Jennifer Ogilvie, who's a professor in the physics department. What she studied when she was in your position, when she was a graduate student at the University of Toronto in the group of Dwayne Miller, was a protein that everybody loves, especially in biophysics. You love it too. I love it too because I wouldn't be able to be moving this piece of paper without it. The protein is called myoglobin. It's a remarkable protein. It's very compact. It's a globular protein. In the middle of it, or sort of in the middle of it, it has a heme cofactor, which is basically an iron porphyrin. We can abbreviate that like this. It's attached into the protein, bound on the bottom by histidine. And then when it's functioning properly, meaning when you're healthy, it will bind oxygen. If you smoke, it'll probably bind carbon monoxide. Okay, and so it turns out there's a differential binding for carbon dioxide and oxygen. And that's one of the reasons why smoking is bad for you. Experimentally, it's much more convenient to put a carbon monoxide as a ligand because it doesn't rebind immediately like oxygen does. After what? After photodissociation. So if you look at a typical absorption spectrum of a heme, there's a very big peak around 420 nanometers and a much smaller peak around 530 nanometers. These are very approximate, but they're okay. This band here is called the Sorey band. This band here is called the Q band. The Sorey band is the very strong allowed pi to pi star transition of the ring that we've talked quite a bit about what happens in conjugated systems. And the Q band is forbidden, but it borrows some intensity by coupling to the Sorey band. So you can excite hemoglobin or myoglobin, heme proteins that have carbon monoxide bound onto them, either with 400 nanometer light or with 530 nanometer light. The actual bands are quite broad, and you have a bit of choice. So what Jennifer Ogilvy did, and other people had done this too, but I mean her experiments were really cool because they used this technique. And actually I like it too because it's not the fanciest experiment in the world, partly because what they did was they used nanosecond lasers to excite in the green around 530 nanometers, which photodissociates to carbon monoxide. And one of the things that's remarkable about heme proteins, first of all, myoglobin was the first protein whose structure was determined by X-ray crystallography. And one of the things that they realized immediately when they looked at the structure of myoglobin, everyone knew that it bound oxygen or carbon monoxide or other small ligands. But when they looked at the structure, it was like there was no way, obviously, for the ligand to get in or out of the protein. So it was almost like the first structure of the protein made it very clear that fluctuations of that structure were going to be absolutely essential for its function. Because if the protein didn't move, there would be no channel in or out for the carbon monoxide or for the oxygen ligand to get in and out. All right, and so they knew immediately from the first structure that dynamics was important. I think that's really poetic because, of course, we appreciate that quite a bit now. Anyway, so what it turns out happens that's really remarkable is when the heme is excited to the excited state and the carbon monoxide comes off, if you look at edge onto a heme, it's flat. This is a histidine on the bottom, what I call the bottom, and the carbon monoxide would be on top. When, in fact, the carbon monoxide comes off, the heme domes and pushes down on this histidine that's here. And that drives a rather large-scale structural change of the whole protein, just triggered by whether the iron has a ligand bound or not. And it's this extreme coupling of a small chemical change into a giant structural change that helps provide a pathway for the carbon monoxide or whatever ligand it is to get out of the protein. And that's pretty remarkable. So when Jennifer's experiment was really cool. So she takes 530 nanometer light, relatively long pulses, but the time to get out of the protein is not ultra fast. Time to break the bond is ultra fast. They also figured that out later on with much shorter pulses. But what they did was a very in some sense, a very simple experiment, which was to excite the protein. And they were probing it, in fact, very far away from resonance. They were probing it at around 1064 nanometers. And believe it or not, using a CW laser, just a sine wave, basically, in the near infrared. And they were just detecting it on a good but ordinary oscilloscope. So what you saw when you did the experiment, triggered by the pulses, because it was using a transient grating geometry, was an increase of the signal, diffraction, and then what they found was pretty cool. There's a phase where it kind of doesn't do that much and then pops. And here's the diffraction efficiency. It's a little bit more complicated. They used an elaborate detection scheme called heterodyne detection so that they could measure the field and really extract the part of the grating that's due only to the change in phase. Now, where is the change in phase coming from? The change in phase is coming from the fact that when the protein is not ready for the CO to leave, it hasn't undergone the structure change, it's more compact. And then as it sort of swells a little tiny bit to allow the CO out, its density decreases. Its volume gets bigger, its mass stays the same, and it takes up more space. That changes the phase. So as the density increases of the molecule, you can actually detect that directly in the diffraction efficiency because you're focusing on the density part or the phase part of the response, not the absorption spectrum, not the typical thing that you measure in spectroscopy, but the effect of the actual volume change of the protein changes the index of refraction in a periodic way because you wrote a grating on the sample. And then they were able to determine that this time scale is about 300 nanoseconds. So it's about a 300 nanosecond period where the carbonyl is kind of like, going around in the protein. Then it leaves and the protein collapses afterwards. This is the ligand escape. And then this is relaxation of the protein after the CO is gone. So it's one of the most remarkable ways of seeing a structure change, obviously not atom by atom, but certainly in real time. This is as real time an experiment as you're going to get. Every single scan that they did was literally a real time experiment, a pump and a transient digitization of the CW laser its diffraction efficiency. Not like the way we do in ultrafast where we stroboscopically repeat the experiment over and over again with different time delays between the pulses. That's not really real time because it takes a long time to scan. This is a great example of using in this case, a phase grating to measure large-scale structural changes triggered by the photodissociation of a small molecule ligand. And it fits into a big story that's been going on since probably the entire history of modern biophysics. Subsequent to this, people used X-ray diffraction to actually look at the atoms as they moved, and all kinds of other nice optical spectroscopy methods. But I still think this is one of the coolest things ever. Maybe it's not the coolest thing ever, but it's pretty up there with coolest things ever. But what is really important, and I want you to make this point super clear here, don't forget the grating. The grating is super important because when you think of a diffraction grating and diffracting from it, I'll ask you, it's very much like the zebra paradox or the zebra parable, right? So if you ask some people whether a zebra is white with black stripes or black with white stripes, the answer you get will be usually dependent on where that person lives and perhaps their cultural heritage. So I'll ask the same question here. In diffracting off of a modulated grating, modulated intensity or modulated amplitude or index of refraction, which is more important, the bright fringes or the dark fringes? Well, of course, the answer is neither one is more important because you can't have one without the other. There's no way to have a bright fringe without a dark fringe. So when you think about nonlinear spectroscopy, which is going to be really about the interference of multiple Liouville space pathways, we're going to be able to write down the mathematical description of how this got bright. And we're going to see that we can write down the mathematical description of how this got not bright. And we're going to see that we need to add those two together. When we say interfering the Liouville space pathways, we literally mean making this diffraction grating pattern. Okay, and so the point is, there is no more significant thing. The dark is just as significant as the bright. You can't have one without the other. All right, and that's a very important way of thinking about the relationship between the Liouville space pathways, how we generate signals, and also, for example, why a transient grating experiment, which has these diffraction grating, and a pump probe experiment, where you chop on and off a pump pulse, are related to each other. Because if I do a transient grating experiment, or a transient absorption, I chop my pump, look at just the transmission of my probe, then put a pump pulse on, do whatever is happening in the bright spot, and look at how that changes the absorption of my probe. And then I take the difference to measure the transient absorption. I ask you, which is more important? The one with the pulse on or the one with the pulse off? And of course the answer is they're both important, because I can't have one without the other. I certainly can't have any difference spectrum with only one thing. All right, so just the way we use a chopper to chop on and off a pump pulse, we're causing the interference of Liouville space pathways when we take the subtraction of those two. Here we're doing the same thing. We have to have this difference in index of refraction in order to get difference in index of refraction in order to get a signal that comes out in a different direction.